And now we are going to see how to use the toolbox to get calculation results into Grasshopper. So, okay, here I have Grasshopper and Rhino, and I also need an RFEM model in which my load cases and load combinations already have calculation results. That's important. So in this case, I'm going to use the same model as we were using, this concrete building, but now it has been analyzed and you can see the results here. So to get the results in Grasshopper, we're going to use these components here, and we're going to start with the get results component. So we get this component here, and we just need to do one thing to get the results into Grasshopper, which is to get a button and plug it here, and we just need to set to press this button to get the calculation results. So let's go for it. And there we go. So you can see how we're importing calculation results here. So we see different things. First, we can realize that these drop-down menus regarding load cases and result types have been filled in. So we can see the load cases here and load combinations. And remember, you are just going to see here the load cases and combinations which have available results. Otherwise, they won't be displayed here. And here is the results type. So for load cases, there is just one standard type, but for result combinations, you can see how you can have here minimum or maximum value type as a result type. Okay, but let's start with the load case number 2, for instance. And it is important also to take into account that I created this component, so it runs with a button. So please, here you should use a button, because otherwise the results won't be displayed until the button is released, which means run must be set to false. Okay, so now we have the load case 2 and standard value type, and of course you are realizing that if you take a look into the Rhino canvas, there we go, we can see how we are getting the model here with our finite element meshes. But this is not just the model, because it is the deformed shape, although you might not realize that, because the scale factor is set to 0 by default. So if we set another value here, for instance 250, we can see how actually we can play with the deformed shape, and our model, yeah, we can exaggerate the deformation if we set a relatively high scale factor like that. So I think the deformed shape looks really nice. So we can see how our beams are being deformed, and our surface elements as well. So everything looks pretty nice by the moment. Okay, so now we are importing deformation, let's say graphical results from our load case number 2, but what other kind of results we can import from RFEM? So in order to see that, we have to expand this menu here, the select results menu. So in this case, we can see that we are importing member forces, surface forces, and nodal reactions, because by default we are selecting all these options. It is important to take into account that I created this component so you could work with load cases and load combinations of very relatively big or huge models. So in case that this import process would take too long, you should just deselect the results that you don't want to import. So if I change from load case number 2 to load case number 1, you can see how it is almost automatically, it doesn't take long for doing that. Otherwise, if I select all results, we need a bit long, okay, to get the results. But let's start, for instance, with member forces. And where are we getting these results? And of course, we are getting these results from the results output parameter. There we go. So for instance, let me get a panel into Grasshopper. And if we connect this output parameter here, we can see, okay, RFEM results, load case number 3, that's right, and available results, member forces. So with the load cases, we are not just selecting the load cases to get our deformed shape from, but also we are selecting the load case that we are going to get the calculation results here from. So in this case, we are getting the member forces. And okay, and how can we analyze the member forces? Because this is very nice, but this is just a panel with very basic information. So to analyze the member forces, we have this other component here, member forces. So we get that one into Grasshopper, and now we just have to connect the results with it, and we can see how it is working apparently. So let's take a look which kind of information we are getting from this component. Okay, and let's start with a Grasshopper panel to see it properly. So number, it makes reference to the member number we are getting the results from. And of course, now we have here forces and moments. So let's take a look into it. And we can see that actually it is a vector. So which means that we have three components in X, Y, and Z. So the first component of our vector, this one here, this value is going to be the axial force. Then y would be the force in the shear force in the y direction, and finally the shear force in the z direction. So there we go. And we can see that it is like a tree structure, 94 branches, which means that we are getting 49 members. And of course, we have to take into account that we have the number 0 as well, so we have 94 results in total. Okay, so for instance, in the first number, we are getting 16 values, and those 16 values make reference to the location, because we can see that for the first member, we have 16 locations that make reference. These are the locations, and this is a number, and it makes reference to the location of the results along the beam. So the first vector would make reference to the starting point of the beam, and so on and so forth, until we get the final point or the final location of that particular member. And of course, since this is a vector, we can also deconstruct it with the deconstruct vector component, and here we get also the results in the different coordinates. So in case that we were just interested in the axial force, for instance, we can get it from this component like that, because we don't care about the shear force. And of course, we can do that with forces, but also with moments. We can take a look here, and since this is a vector as well, we have the torsional moment in the x direction, then the bending, in this case it is 0 of course, then the bending moment in the y direction, and the bending moment in the z direction. So there we go. So those are the result of my member forces. And which other results can we analyze in Grasshopper with the toolbox? So let's take a look to the next one. Next one, in this case, the nodal support forces. Let's get this component into our canvas. And however, if we try to connect the results here, we should get a warning, which means no results available. And of course, the reason for that is that we need to check nodal reactions. And again, the reason for these checkboxes was to optimize the execution time. So if we couldn't need these results, we could just deselect this box so that the execution time could be reduced. But in case that we want to analyze the nodal reactions, we can of course activate it and get this component here. So this is very similar to the member forces. First we have the support number. There we go, support number. And we also have the location. And this is a tree because we might have nodal supports with different locations. We can get a point parameter to see where those reaction forces are taking place, and we can see that we are selecting the nodes here, which are basically the base points of our columns. We can also get the reaction forces as vectors regarding forces and moments. So moments are of course 0 because we have like pinned supports, and we can deconstruct the forces as a normal vector as we were seeing before with our members. Okay, and finally, we have already seen member forces and other reactions, and let's take a look to surface forces. So if we select this option here, now we should be able also to analyze surface forces. And in order to do that, first we need plenty of space, and then we need to get this component, the surface forces component, into the Grasshopper canvas. So there we go. And we can see that it is a huge component, but we just need to connect the results object here to analyze it. So we can see how we can get member forces with as many options as we have in RFEM. And there we go. So for instance, we have also the number of the surface that we are analyzing, and also we have the points of the finite element node in its surface. and then we can analyze like the forces in those locations, so like the axial force number 1, number 2, and so on and so forth. And now this can get really interesting, because we are getting numerical results here, and we're also getting graphic results here from this component, so we can combine them to analyze our results in a graphical form. And let's try to do that. And what I mean, for instance, let's try to display the bending moments along the first axis here graphically. So of course this is like a numeric output, but we can use this output to create a gradient. That's right. So we can get the gradient component here, and let's get perhaps a more interesting one. So this gradient type, and in the gradient we need to specify a input parameter, and this parameter needs to be between 0 and 1. So to choose the right values, and this, of course, and these forces, they are not going to be between 0 and 1. And the input parameter t needs to be a parameter between 0 and 1, of course. So since we are getting all kind of values here from these bending moments results, what we need to do is to remap these numbers. So again, we need the remap numbers component, and here we have to provide the input values, and we are going to remap them first with the source domain, which would be the extreme values of our bending moments. So in this case we can see that the extreme values, so the first surface would have values between -17 and 20, and we are going to use them to remap those values. So now these values would be between 0 and 1. Let's take a look how that looks like. And there we go. Now we can see how all the values are between 0 and 1. So we are now ready to connect this thing here. And now we should be able to use the mesh colors component. So there we are, and these are our colors. And of course, this is like a tree structure, because we also need to graph the mesh input that we are going to get from here. So let's go for it. And now we can see how we are getting our results graphically into our deformed shape here. So we can still play with the gradient, and we can see how we are getting the results as a gradient anyway. So let's take a moment to think what is happening here. So first, this is happening because the order of the meshes is the same order as we provided here for our tree structure of results, but furthermore, the list items of each branch make reference to a member node that are sorted in the same way as the finite element meshes in RFEM. So it is important to take into account that I consider that in order that we could get the calculation results here. And of course, imagine that you were saying, and of course you can play with the gradient here and so on and so forth, but you can say, okay, but I want to, let's say, not show those big values that much, because perhaps we are not considering other results, or we are neglecting them because of the strong influence of these big values. So what we could use is like a scale factor to get rid of those big values. Let me explain what I'm trying to say. So if we get the deconstruct domain component here, we can multiply it by a scale factor between 0 and 1, hopefully. That's right, and there we go. There we go, and we can construct this domain once again. Domain, so this is the first value, this is the second value, and this would be the new source domain. And okay, so if we set 1, we are getting the same results like before, but if we make this value lower, we would be, let's say excluding these peak values from our gradient. So you can see how now we can see a much more interesting gradient for our structure. And this makes reference to the bending moments along the first axis, let's say. So this could be basically another way to analyze the calculation results from a Grasshopper model into RFEM with the parametric finite element toolbox. And finally, let's take a look into the other options that we have with this get results component. So we're basically selecting the load cases and load combinations with these drop-down menus here. But what we can also do is to use the override option. So here we need basically to specify the load case with a panel or basically in a text form. So let's use load case number 1. And we also need to specify the result type that we want to import. So let's get a value list for that. And once we connect the value list here, this is similar to other Grasshopper components of the toolbox. You can see how the drop-down menu gets updated with the actual names of the result type. So let's, for instance, choose a standard value type because it is a normal load case. So if we do this, we can see how we are importing the results here. Okay, perfect. And this is very interesting because, of course, it allows you to import results like parametrically without the drop-down menus. And this is basically also the only way to import results from two different load cases at the same time with the same component. So if we do something like this, we can see how we are actually importing like two different load cases here. So there we go. You can see that we have two different deformed shapes, and of course this might be interesting not just for analyzing the deformed shape but for analyzing different results, because we can see how we are getting the calculation results for two different load cases, right? Load case number 1 and load case number 2. So in case that we are importing the results from a load combination, we should need to specify this keyword like load combo. So if I try this, I'm going to get an error because there is no load combination in the model. So it says load combo number 1 has no result, provide valid load case. And in case that we were trying to get results from a result combination, we should use this keyword here, like result combo. And if we do that, we need to specify the result types here, which should be, like for instance, maximum value type, because this is a result combination. That's right. So there we go. And we can, of course, play with the scale factor and so on and so forth. And that would be the other way to importing calculation results into Grasshopper, not with the drop-down menus, but parametrically with these input parameters here, in case that might be interesting for you.